All right, moving on with infinite functions. I left you with the applied example in the last video with part C, so that's right where I'm going to go into. Okay, part C. Part C of this problem. What population should Scott plan for in the long run? This is the first problem where we don't simplify using algebra. This is the first problem that we actually use calculus. When it asks in the long run, that means what happens as time increases indefinitely, meaning as time approaches infinity, as our time gets larger and larger and larger. Well, we just learned how to take infinite limits, the limit as t approaches infinity, of our function, of p of t. But we can plug in what p of t is, the limit as t goes to infinity of 40t over t squared plus 10 minus 50 over t plus 1 plus 70. Now, so far, the infinite limit examples that we've had was one polynomial function or one rational expression. The problem here is we see that we have more than one fraction, so how do we handle it? There's actually two ways to go about it. The harder way is to come up with the least common denominator and make this into one fraction or one rational expression. The easier way is actually just to look at each piece separately. Now, I'm going to write this step out just to show you that we can simplify it this way, but I wouldn't expect to see this on your homework or anything like that. So really, I can simplify this as a limit as t goes to infinity of my first fraction, 40t over t squared plus 10, minus the limit as t goes to infinity of my second fraction, 50 over t plus 1, plus the limit as t goes to infinity over 70. So I can just take the limit of each of these pieces individually. Let's start with the first piece. We should know what the answer is by looking at the end behavior or our face case. We have a degree 1 in the numerator, a degree 2 in the denominator, which makes me happy. Means I have a horizontal asymptote. If I were to officially compute this, I would need to divide every term by the highest degree of t in my denominator, which is t squared. So I take my top piece and divide it by t squared. I take this guy, divide it by t squared, and I take this guy and divide it by t squared. Now, if I simplify this, this gives me the limit as t goes to infinity of 40 over t over 1 plus 10 over t squared. But we have that property that says if I'm looking at infinite limits at infinity, and I have a constant over my x, or in this case my t to some power, that piece goes to 0. So this piece goes to 0, this piece goes to 0, and so basically I have 0 over 1 plus 0. And anytime we have a 0 in the numerator, that just simplifies to be 0 in itself. So the limit of my first fraction here gives me 0. Now I have to do the same thing with my second fraction. I look at the highest exponent of t in the denominator, which is just t, and I divide each piece by that there. So when I simplify this, I have the limit as t goes to infinity of 50 over t over 1 plus 1 over t. And again, anytime I have a constant over t to some power, that piece goes to 0. So this guy goes to 0, this guy goes to 0, which leaves me with the exact same thing, minus a 0 over 1 plus 0. So that gives me a minus 0. Now, I should have known that this piece was going to approach 0 as well, because again, I look at my end behavior, my face case. The degree of my numerator would be 0. the degree of my denominator would be 1, so my numerator would be less than the denominator, and of course that's going to approach 0 overall. Now my last piece, the limit as t is approaching infinity of 70. This is the easiest one yet because I need to plug in infinity for all of my t's of my function. But notice I don't have any t's in my function, so I don't have any infinities to plug in. So that piece just simplifies as to what it is, plus 70. So my overall answer, 0 minus 0 plus 70, that of course gives me 70. So if I go back up to here in my problem, what happens in the long run, as t approaches infinity, that means our limit as t approaches infinity of this function is going to approach 70. Now I have to label it because it's a word problem. I'm talking about my p of t here, my population. What happens to my population in the long run? Well, my population approaches 70, or in thousands, 70,000 people. So now you can see why limits at infinity or infinite limits actually have an effect on real life situations. We want to know what happens in this case to populations overall or any other type of business type of problems in the long run. What's going to happen indefinitely. And this finishes up my infinite limit segment.